All right, this is the part 2 of L'Hopital's rule. So we do have other indeterminate forms, and these are all basically based on that, and you'll see why when we do these, that we can use these to basically rewrite them into this form and then reapply them. So let's look at our first one. So our first one we're going to be using is our indeterminate products. These two right here. Basically, we're multiplying. So if we're multiplying a 0 by an infinity, doesn't matter the order, then we can use L'Hopital's rule because we're going to be able to rewrite them. So if I were to plug in infinity, the first one would become infinity, but the other one's a fraction, so it's e to the negative infinity, and that's our exponential decaying towards 0. So you can see it fits our product, 0 times infinity, which means we can rewrite it. Doesn't matter which you pick. So we're going to pick the one that's the negative exponent right off the bat because it's just easier to move them down. Now you do have options. You could put the radical x on the bottom and keep the e to the negative x over 2 on the top. Or you could put what we just did was here. What's happening here is if you put it on the top like this, we get infinity over infinity. This is now an exponential. So it goes off to infinity over infinity. If I had done it the other way, and I put the radical x on the bottom, that would become 1 over radical x. And then this would just stay up here like this. And then this would equal 0 over 0. And so you see it fits both methods. One of these two, though, is the better method, and that's this one. So you basically want to just write it and try it. If it works, great. If it doesn't, you revert back and you try the other one. So this is the one that we are going to use. So since it meets our condition, let's take our derivative. So this would be 1 over 2 rad x for the top, and the bottom would be e to the x over 2 times a half. So I rewrote this as x to the half, brought it down, and then put a radical x. And the other one is e to the x over 2, so that would be e to the x over 2 times the derivative of the exponent, which is a half. All right, now let's rewrite and see what we get. So the limit as x approaches infinity would be 1 over, and you can see that there's a 2 on the top, and we're dividing by a half down here. So if I bring the 2 down, it's just going to cancel. See, it's a division. And so we end up with radical x e to the x over 2. You can do some simplifying on the side if you want. I don't have a lot of room. Now if we apply it and we plug infinity into our two parts, this would go off to infinity, and this is an exponential, so it also goes off to infinity just like it did before, which means this goes to 0, because this is going off to infinity. The entire fraction becomes 0. Remember, that's our fraction. There you have it. All right, let's try another one. This one now is going to be the next one in the step, which is our infinity minus infinity. So if you plug in 0 into cosecant, as we approach 0, where it's the reciprocal of sine, it's going to be infinity minus infinity. And you can use your calculator if you want on this, but sine is our denominator, so that's why we're going off to infinity. So now L'Hopital's rule still says that we need it to be in this form. This just means, this indeterminate form means that we can rewrite it in this form. So that's what we're going to do. We're going to take the limit. I'm going to zoom in now. So we're going to take the limit as x approaches 0. And then we're going to write it as a reciprocal. So this would be 1 over sine x minus cosine x. Just erase that. Cosine x over sine x. And then we add them together. So this would be 1 minus cosine x over sine x. And now you can see that this, as we plug in 0, right, that would be 1. 1 minus 1 is 0. And then sine of 0 is 0. So we get our indeterminate form that we wanted, 0 over 0. So now we take limit as x approaches 0 and we take our derivatives. So that would become sine x on the top, cosine x on the bottom. And then we rewrite, this is just tangent x, which we could have left it that way as well. That just becomes sine of 0 is 0 over 1. Tangent 0 is 0. And there you go. So if you see an infinity minus infinity, it just means that we can take it back, that it's a good indeterminate form. Let's try to get it back into that form. All right, let's move down. So now our next one, 0 to the 0. So if you see, if I plug 0 in this, I get 0 to the power of 0. And remember, L'Hopital's works with left-hand and right-hand limits as well. So now, if we take this like that, so with the last 3 that we have, our indeterminate powers, you can see I got 1 of each here, so you can get them all. We're starting with 0 to 0, 0 to the power of 0. What we're going to do is this little trick. We're going to say that we have the limit as x approaches 0 plus, and we're going to call that inside y. So we say y equals x to the rad x. And you can pick any letter you want. You can pick t, you can pick f, whatever you want. We're just calling it y. Now, if we take the natural log of it, we end up with the natural log of x rad x, which we can bring in front. So it's rad x ln of x. So if we rewrite this, we get the limit as x approaches 0 plus of e to the ln of y. That still means the same thing. So e to the ln of y would be y. The y is the x rad x. So now what we can do is find the limit of the natural log of y and just place it here and take an e to the power. So that's what we're going to do. So this is our focus, but we're going to use this down here. So we're going to go the limit as x approaches 0 plus of rad x ln of x. And if we plug in 0, you can see that we get 0. And this is 0 from the right. So our natural log with 0 from the right would be 0 and infinity. That's our product. See? See how it's working now? But what we have to do is rewrite it. Now, if we put the ln on the bottom, it makes it horrible. So what we have to do is actually put the rad x. So we end up doing this. We're going to put it's 1 over rad x. I'll just take it slow. Like this. So this would be the limit as x approaches 0 plus of the natural log of x over x to the negative 1/2. And now if we plug them in, this again is this. So that's infinity and infinity. It's giving us what we needed, infinity, infinity. So now we can take the derivative. So the limit as x approaches 0 plus, this would be 1 over x. This would be negative 1/2 x to the negative 3/2. And then we simplify. So this is limit as x approaches 0 plus. And then this would now move up, that would move down, and the negative 2 goes to the top. So we end up with this negative 2 x to the 3/2 over x, which is the limit as x, I'm going to zoom in, approaches 0 plus of negative 2x to the, and then 1 take away from 3/2 is 1/2. So now if you plug in 0, we get 0. So whether you're going from the left or the right, it would have been 0, but we get, so actually it's a square root of x. So yeah, we do have to come in from the right. Okay, so what we're saying is this is our ln of y right here. So we have this is the limit as x approaches 0 plus of e, and I'm going to write it up there at rad x ln of x. And we know that this is its part right here, that goes to 0. So it's e to the 0, which is 1. So that is our limit. All right, just this can be confusing, so we're going to do it 2 more times because we have 2 more different situations going to happen. So the next one is the infinity to the 0. So if we plug in infinity, you can see that this becomes infinity, and then the exponent itself is a 1 over e to the x, which means it's a 0. So that is our form there. So we're going to do the same thing that we did before. We say y is equal to x e to the negative x. And then that means we get ln of y equals ln of x. We're just ln'ing both sides, e to the negative x. And we can bring that e to the negative x down. Okay, so now we say the limit as x approaches infinity of our x e to the negative x. Well, that is our limit as x approaches infinity, and we're calling that y now. So that would be the limit as x approaches infinity of e to the ln of y. And then that's what we have here. So up here, we actually replaced it. What I'm going to do now is just say ln of y down here and go from there. So the limit as x approaches infinity of the natural log of y is the limit as x approaches infinity of e to the negative x ln of x. So you've got to still make sure, you still need to make sure that you are showing limit and you're showing connection between every single one. These are like little proofs. You can't just say, oh, answer. You've got to have all of your work. So even though this is our main step, we had to show that the rad x ln of x approached 0 so that we can use it. So now we have to see what the ln of y here is going to become. And you can see it now. We have that e to the x ln of x. It's very nice and quick now. This is giving us what we need, because if you just use that little e to the x just like before, we get this. And we actually did one very, very similar to it for the very beginning. You can see that that's the rad x. It gives us the same kind of idea that a natural log is going to give us. So if we zoom in here and we go, well, we already know that that is going to go off to infinity, and that's going to go off to infinity, so we can use L'Hopital's. So the limit as x approaches infinity, we have 1 over x, e to the x, and then we put them together just like we did above. See, the more you do of these, the more you go, oh, I remember doing this before, because it's the same tricks. The same things appear over and over again. And so that's that same basic idea. That bottom is going to get really, really massive, causing this to go to 0. And now we can go back to our main proof that we're doing for our limit. It's a horrible star. And so the limit of ln of y as x approaches infinity is just 0. So this becomes e to the 0, which is 1. And there we have it. Now they're not all going to be 1. So let's try another one where it's not 1. But the same idea, if I were to plug in 0, I'm going to get here 1, right, to the infinity. See, that's the next one, 1 to the infinity. So this is 1 to the infinity, because as x approaches 0, for this 1 over x, it goes to infinity. Remember our rational. All right. Left and right. All right. Okay, so we do exactly the same thing. We say y equals, here, why am I in black now? Let's go back. All right, y equals 1 minus 2x to the power of 1x, 1 over x. That's just like before, see? And then now we can say that our ln of y is equal to, I'm going to do this all in one step now, 1x, 1 over x ln of 1 minus 2x. And we come back over here, and we say the limit as x approaches 0 of y would be the limit as x approaches 0 of e to the ln of y, see, just like before. And now we have our ln of y. So we go limit as x approaches 0. See, they're all the same. You just have to practice with them. All right, a limit of ln of y would be the limit as x approaches 0 of 1 over x ln of 1 minus 2x. And then we rewrite it, the limit as x approaches 0 of ln of 1 minus 2x over x. And then now you can see that if we plug that in, that would be 0. So as we approach 1, we're approaching 0, and that's 0. So we're getting 0 over 0. We can use L'Hopital's rule. So limit as x approaches 0, this would be 1 over 1 minus 2x. This is now chain rule. So derivative of the inside would be negative 2. Don't put the x on there. It's just negative 2. And the derivative of the bottom is just 1. All right, so this is the limit. I'm going to do a little simplifying. Not that you really have to on this one. This would just be negative 2 over 1 minus 2x. And as you can see, that's just negative 2. So as x approaches 0, this would become 0. That'd become 1. That's negative 2. And there you have it. So now if we stop there, we mark the whole thing wrong. We still have to go back to our main one that we're trying to prove and plug it in. So the limit as x approaches 0 of this, well, we already know now the top. Why am I doing this in 0? We already have it. So e, and then the limit as x approaches 0 of ln of y is negative 2. And so I like to rewrite it as 1 over e to the 2, just because I don't like negative exponents. And there is your answer. So you can see each of these as the power ones. So we have 0 to 0, infinity to 0, and 1 to the infinity. When you see them, you're going to try the y equal. Now again, it doesn't always have to use it, but your steps are always the same. This is number 1. I'm going to put them in red. Number 1. Number 2. and then number 3, we rewrite it. Now, I like to write number 3 first and then come back and finish it, but it's number 1, and then we prove number 2, and then we go back to 3. We do number 1, we prove number 2, we back to 3. Now, always make sure that the condition is there, the indeterminate form is given that you need. And then now, if you see the difference one, you want to always make sure you just basically add them together or subtract them together, subtract in this case, to get them back into that fraction. And if you were given the power form one right here, make sure you still write them as a fraction. So you have the option of bringing the second term down or bringing the first term down. These are the two situations that you can do. One will work better than the other. So if you were to try this one, you would notice it's not as nice as this one.